Myself Akhilasri. Today my seminar topic is combinational logic circuits. Now we can discuss about the combinational logic circuits. Combinational logic circuits are digitally circuit where the output depends only on the present inputs, not on any past history or memory. In other words, they do not have storage elements like flip-flops. Think of them like a vending machine without remembering your previous choices. You press a button input and instantly the machine gives the corresponding item, that means output. Key features: no memory. Outputs are not affected by previous inputs. Output equals to a direct function of the inputs. Built using logic gates, that means AND, or, not, NAND, NOR, XOR, XNOR. Now we can discuss about the examples of combinational logic circuits. For examples, adders. There is a different types of adders like half adder, full adder, and subtractors. Multiplexers. Multiplexers, it is denoted as capital MUX, and demultiplexers, it is denoted as capital DEMUX, and encoders, decoders, and operators. These seven are best examples of the combinational logic circuits. And now we can discuss the procedure of combinational logic circuits. Here's the general design procedure. Step 1: Problem definition. Understand the requirements of the circuit. Identify the number of inputs and decide the outputs. Step 2: Construct on truth table. List all possible input combinations. Write the corresponding outputs for each case. Truth tables from the backbone of the design. Derive Boolean expressions. Step 3: From the truth table, write Boolean expressions for each output using sum of minterms or product of maxterms. And step 4: Simplify the Boolean expressions. Use algebraic simplification of K-maps, that means Kargak maps, to reduce the logic. This step minimizes the number of gates and complexity. Step 5: Implementing with logic gates. Draw the circuit diagram using basic gates. The basic gates like AND gate, OR gate, NOT gate, or universal gates, that means NAND gate or NOR gate. Choose ICs if needed. Step 6: Verify the circuit. Recheck the truth table with your design. Ensure the output matches the required specification. Now, example. Design of half adder. Number 1, problem. Add two 1-bit numbers. Number 2, inputs A, B, and outputs equals to sum and carry. Step 3, truth table. 0, 0. That means sum equals to 0, carry equals to 0. 0, 1. That means sum equals to 1, carry equals to 0. 1, 0. That means sum equals to 1, carry equals to 0. 1, 1. That means sum equals to 0 and carry equals to 1. Step 4, Boolean expressions, that is sum equals to A XOR B, carry equals to A into B. Number fifth one, simplification. Already it's minimal. And the sixth step, implementation. Implement means use XOR gate for sum and AND gate for carry. Classification of combinational logic circuit. Classification of combinational logic circuits. Number 1, arithmetic circuits. Perform arithmetic operations of adder, full adder, of subtractor, full subtractor, parallel adder or parallel subtractor, arithmetic logic unit. Number 2, data routing circuits. Control the flow of data. Number 1, multiplexer. Number 2, demultiplexer. Code converter circuits. Binary to gray code converter, binary to BCD converter, BCD to XS3 converter, 7 segment display decoder. Step 4, decoder circuits. Convert binary input into one active output, that means n to 2 to the power of n decoder. For example, 2 to 4, 3 to 8, 4 to 16. These three is undergo the n to 2 to the power of n decoder, that means decoder circuits. Step 5, encoder circuits. Perform the reverse of decoding, that means many inputs to binary code. 8 to 3 encoder, decimal to BCD encoder, priority encoder. And next we can discuss the step 6. Step 6, comparator circuits. Compare two numbers and indicate relation. 1 bit comparator, 4 bit comparator. In short, combinational circuits equal to arithmetic plus data running plus code conversion plus decoders plus encoders plus comparators. Now we can discuss the example of combinational logic circuit in detail. In topic of combinational logic circuit, one of the simplest but most important combinational logic circuit is off adder. Off adder is the best and simplest example of the combinational logic circuits, and it is one of the most important example of combinational logic circuit. For example, off adder. Number 1, definition. A off adder is a combinational circuit that adds two single bit binary numbers and produces two outputs. Sum, it is denoted as capital S. Carry, it is denoted as capital C. Step 2, inputs and outputs. Inputs means A, B and each can be 0 or 1. Outputs, sum equals to A XOR B. It is used in XOR gate. Carry, that equals to A into B. It is used in AND gate. Now step 3, truth table. The truth table is indicated as the columns of A, B, sum, carry. 0, 0, sum 0, carry 0. 0, 1, sum 1, carry 0. 1, 0, sum 1, carry 0. 1, 1, 0, sum 0, carry 1. The sum works like XOR. It's 1 only if inputs are different. The carry is 1 only when both inputs are 1. Step 4, logic diagram with neat sketch. Use XOR gate for sum. Use AND gate for carry. Now we can discuss it about the applications of combinational logic circuits. Used in binary addition inside computers, basis for building more complex circuits like full adder, arithmetic logic unit, ALU, etc. So this is a detailed example of combinational logic circuit. Now we can discuss the just brief explanation of combinational logic circuits. Combinational logic circuits are digital circuits where the output depends only on the present input values, not only any past history, like no memory. They are built using basic logic gates like AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate, XNOR gate. Inputs go through gates, produces outputs instantly. For example, an adder circuit adds binary numbers output changes immediately when input change. Now we can discuss the key points of combinational logic circuits. No feedback or storage elements. Faster because they do not walk for previous states, and it is a less complexity, and it is used in many digital systems like arithmetic operations, data transfer, and decision making in digital systems. And it is so useful to data transfer. That means encoders and decoders for coding, decoding information, and decision making. Comparators to check greater than, equals, or less than. Then data selection. The combinational circuits are more useful to data selection like multiplexers, demultiplexer for routing signals, and data conversions. Data conversions is also useful to the combinational logic circuits. That means binary to gray, gray to binary, or BCB, and 7 segment display circuits, and also logic implementations. Building blocks for ALUs. ALUs means arithmetic logic units, and arithmetic operations are also already we have discussed arithmetic operations. In simply, arithmetic operation means adders, subtractors, multipliers in CPUs, and it is basically the backbone of calculators, computers, digital watches, and even traffic light controllers also. And it is the brief explanation of combinational logic circuits. And thanks for watching. Thank you to all.